Welcome everyone. Thank you for joining us for today's webinar. My name is Farah Karimais, your MC. Welcome back to Infrastructure Connect Digital Series, a series of activities from Indonesia Infrastructure Week, Konstruksi Indonesia, and Beton Indonesia 2020. This event is accessible through the Digital Infrastructure Connect platform from 21st October to 3rd December 2020, and register yourself on infrastructureconnect.id to get an access. Please allow me to inform you that during the webinar event, participants can ask questions through the Q&A feature, which is located at the bottom of your screen. Please mention your name, your company or institution, and also the question addressed to which speaker through the Q&A feature. You can ask questions in Bahasa, and we will translate and answer in English. And the moderator will select some of the questions that will be delivered to the panelists. There will be 3 souvenirs from the Embassy of Canada for 3 best questions, and the winner will be announced in Indonesia Infrastructure Week Instagram at Indonesia Infrastructure Week and contacted by the Embassy of Canada. And last but not least, the rules for obtaining e-certificate and presentation material will be delivered at the end of the event. And now, before we start the webinar, please join me to welcome Mr. Teshome Nkrumah. He's a Canadian Trade Commissioner and Deputy Trade Program Manager at the Embassy of Canada to Indonesia and East Timor, where he leads a team of trade professionals supporting Canadian businesses in the infrastructure, clean technology, financial services, aerospace, and defense sectors. Mr. Teshome, the screen is yours. Sorry, Mr. Teshome. You need to unmute. Thank you.
Thank you. Terima kasih, Ibu Farah. Bapak-bapak dan ibu-ibu, good morning, selamat pagi, dan selamat datang di acara webinar kami. On behalf of the Canadian Trade Commissioner Service and the Embassy of Canada to Indonesia, it is my pleasure to welcome you to this webinar. It is indeed an honor to have with us representatives from Canadian companies, Carbon Cure Technologies, Geotech Scientific, and Carbon Upcycling Technologies. Let me also express my deepest gratitude to Dr. Hari Nugraha Nurjaman, Chairman of the Indonesian Association of Experts of Precast and Prestress, for agreeing to be our moderator today. This webinar promises an insightful discussion on sustainable technologies that reduce the carbon footprint in the concrete industry and fosters a local circular economy. As you know, concrete is everywhere. It is the largest manufactured product on Earth by mass. And it lies at the intersection of Indonesia's climate change and development goals. Indonesia, as a modern and developing country, requires a built environment that is unimaginable without the widespread use of cement-based materials that allow complex construction anywhere and at low cost. Yet, production of this versatile and ubiquitous product accounts for around 8% of global CO2 emissions, about half of which results from the chemical reactions inherent in the production process. In Indonesia, it is estimated that 31 million metric tons of 610 million metric tons of CO2 emissions in 2018 were from the manufacture of cement alone. Friends, as you know, climate change is one of the greatest challenges of our time. And as parties to the Paris Agreement, Canada and Indonesia share a commitment to combating climate change by limiting global warming to well below 2 degrees Celsius, while pursuing efforts to further reductions of warming to around 1.5 degrees Celsius. Indonesia has pledged to reduce its greenhouse gases emissions by 29% independently, or by 41% with international assistance by 2030. Sustainable concrete, we submit, which uses different technologies and materials for producing cement, can reduce CO2 emissions by between 50 and 80%, depending on the technology used. So, hastening the adoption of sustainable concrete globally is one important path to help countries combat climate change. Today, you will meet some Canadian companies, and we're very pleased because Canada and our companies have been global pioneers in sustainable concrete and other game-changing clean technologies that help fight climate change. For the past 3 years, at least 12 Canadian companies have been named to the prestigious Global Clean Tech 100 list, which identifies the most innovative and promising private clean tech companies around the world. The 3 companies represented here today are examples of such Canadian excellence in clean tech innovation and leadership. Carbon Cure was awarded Company of the Year for North America in January 2020 Global Clean Tech 100. Geotech is among the top 12 industry and construction IoT innovators worldwide for 2020. And Carbon Upcycling Technologies is known for its revolutionary solutions, including reusing fly ash as an additive to build stronger and more efficient cement and concrete. Canadian clean technology companies are also commercializing exciting innovations in lithium-ion battery recycling, energy storage, carbon capture, utilization and storage, and waste to resources. These companies and their technologies are leading the transition from an economic model based on take, make, and dispose to a circular model where goods are produced, distributed, and consumed in a way that retains the value of the products and resources for as long as possible. This shift also holds the promise of increased resource productivity, creation of new jobs, and reduced negative environmental impacts. So like Indonesia, Canada continues to be faced with the challenge of developing its built environment sustainably while meeting its citizens' expectations of quality, value, and durability. This webinar is an opportunity to continue that important dialogue about solutions. We also see it as an opportunity to share with our Indonesian friends Canadian best practices and lessons learned, specifically in the concrete industry. And so, without further ado, thank you all very much for participating, and I wish you a very fruitful discussion. Terima kasih.
Thank you very much, Mr. Teshome, for the opening remarks. Now, ladies and gentlemen, today we will be discussing about climate change adaptation in the concrete industry. And today's webinar will present speakers from Carbon Cure, From Carbon to Simply Better Concrete, Geotech, Revolutionizing Concrete Testing, Carbon Upcycling, The Waste of Today, Building Tomorrow. And present with me today as moderator, Bapak Hari Nugraha Nurjaman, Chairman of IAPI, Ikatan Ahli Pracetak dan Prategang Indonesia, atau Indonesian Association of Precast and Pre-Stressed Engineers. And now without further ado, I will turn the time over to Bapak Hari to lead this discussion. Pak Hari, the screen is yours.
Thank you, Ms. Farah. Good morning, everybody. Good morning also, 3 distinguished guests from Canada. And one of you is in the Cape Town, yeah, South Africa, yeah. Well, welcome to Indonesia by digital. Yeah, we talk about the concrete and climate change in this morning. Yeah, Indonesia, as just mentioned, is one of the country that follow the Paris Accord. So we have so many targets, and yeah, we hope we in the concrete industry can give a contribution, yeah, to reduce the climate change. So the first speaker is the Mr. Kaya Salowski from Carbon Cure. He's a VP of Business Development responsible for accelerating carbon cure growth outside of Canada and US. With 25 years experience developing world-class sales organization to support partner with win-win strategies. His global industry background includes specialty concrete admixtures, building materials, transportation, logistics, manufacturing, and telecommunication. Based in Vancouver, Canada, Kaya is excited to make sustainability profitable for ready-mix, precast and masonry, concrete producer in support of carbon cure missions to reduce CO2 emission by 500 megatons annually. So, Mr. Kaya, time is yours.
Thank you so much for the introduction. It's a pleasure to join you at a distance in support of our common mission and objective. We do have a short pre-recorded webinar that I will deliver, and I will be available towards the end of this series to answer any questions that you may have. So thanks again for the opportunity. Hello, everyone. My name is Kaya Solovsky. I'm the Vice President of Business Development for Carbon Cure Technologies. It's my pleasure to be with you today to deliver a presentation entitled Reducing the Carbon Footprint of Concrete. The agenda will start with some background on Carbon Cure, a brief explanation of why we've chosen concrete as our target market, our technology offering and value propositions, our market impact to date, and then a brief summary. So who is Carbon Cure? Carbon Cure's vision is to make the introduction of carbon dioxide into concrete the global standard for all production. Our mission is to reduce 500 megatons of carbon dioxide per year. That is equal to taking 100 million cars off of the roads. We were founded in 2012 by our CEO, Robert Niven. We are currently in use, in production, in over 250 concrete plants in North America, Latin America, and Southeast Asia. We were voted in 2020 as North America's Clean Tech Company of the Year. We are investor funded and are very proud to have all of these companies as part of our network of investors. Most recently, Amazon, Microsoft, Taronga Group, and 2150 joined a broader group of investors that was anchored by Breakthrough Energy Ventures, which is chaired by Bill Gates of Microsoft. Why do we use concrete? I think most people recognize that concrete is used very frequently. If we look at all of the other industrial materials that are used by human beings, concrete by far outweighs all of the others. So why does humanity choose concrete as a building material? It's relatively low cost. It's extraordinarily resilient. It can be recycled at the end of its life, whereas wood, as an example, cannot. It's tremendously versatile, dependent on geology, geography, altitude, weather, soil conditions, or shape. You can't get more flexible than concrete. And the ingredients are very local. Aggregates are everywhere. Water is relatively plentiful. And cement's raw ingredient, limestone, is frequently occurring. So our technology offering and value propositions are very nicely explained in the following video.
CarbonCure is clean technology that allows ready-mix concrete producers to reduce costs, deliver greener concrete, and win more business. CarbonCure works by injecting recycled carbon dioxide, CO2, into fresh concrete during mixing. Once injected, the CO2 undergoes a chemical reaction where it transforms into a mineral, improving the compressive strength of the concrete, which then enables the reduction of cement content in mix designs while maintaining strength requirements. The CarbonCure technology is made up of two boxes: the control box, which is the brains of the operation, and the valve box. The valve box connects to a CO2 tank and delivers a metered quantity of CO2 into the concrete mix. The CO2 is stored on site in a pressurized tank provided by industrial gas companies. The control box monitors the performance of the valve box system in real time and feeds back all usage data to the CarbonCure command center. The control box software integrates seamlessly with all existing batching software, so adding CO2 into a mix is just like adding an admixture, meaning no impact on batching or loading cycle time. Transfer hoses deliver liquid CO2 from the supply tank to the CarbonCure valve box, which is at the plant loading area. The valve box then meters and delivers a known amount of CO2 into the concrete mix based on the cement content of the mix. The CO2 automatically injects into the mix once roughly half the cement and water contents have been discharged. While liquid CO2 is stored in the tank on site, the CO2 that comes into contact with the concrete is actually in a solid and gaseous state, similar to dry ice or snow. It changes state once it leaves the CarbonCure valve box due to a significant drop in pressure. Upon contact with the mix, the CO2 undergoes a chemical reaction and converts into a mineral, calcium carbonate, which makes the concrete stronger. Plus, what was once CO2 is now eliminated, never to be re-released into the atmosphere, even if the concrete structure is demolished. Concrete made with CarbonCure has no differentiating factor from concrete without CO2 in it. Fresh and hardened properties are not affected. Any mix design can be adjusted to include an optimized dose of CO2 and a reduction of cement content without compromising the concrete strength. This means CarbonCure mixes can be used for all commercial and residential applications. Every cubic meter of concrete produced with the CarbonCure technology saves an average of 17 kilograms of CO2 emissions from entering the atmosphere. An average high-rise building built with CarbonCure would save approximately 680,000 kilograms of CO2 emissions, which is equivalent to the carbon absorbed by 360 hectares of forest in a year. Reduced cement content means reduced costs and a reduced carbon footprint, and more business from the green building markets. With CarbonCure, concrete producers can create a legacy of sustainability in their communities while attracting and retaining employees who want to work for an employer that does something positive for the environment. Technology costs are offset by cement savings, one-day installation of the technology without disrupting operations. The technology can be retrofitted onto any wet or dry batch ready-mix plant. Seamless integration with your existing batching software means it's as easy to install as it is to use, all provided with the ongoing guidance and support of a dedicated CarbonCure technical services team member. Join the growing network of concrete producers who are using CarbonCure in hundreds of ready-mix plants around the world. It's simply better concrete.
And now I'd like to tell you a bit about our market impact to date. Our technology adoption is still in the early days. The countries in orange are countries that have either adopted the technology through our producer partners or where we have signed commercial agreements with distributors or have secured regulatory approval. So as you can see, we are still looking for partners in much of the world. The environmental impact and the production impact are growing every day. We have poured almost 6 million cubic meters of carbon cure concrete to date. We've been implicated in many different types of projects, residential, commercial, even departments of transportation are using us now on roads and bridges in the United States. And it's important to note that we have been successfully used across all exposure classes and applications of concrete. The environmental benefit is now almost at 90,000 metric tons of CO2 avoided and continues to grow every day. So in summary, the addition of waste or recycled carbon dioxide into concrete has a neutral impact on all of the key fresh and finished properties. So if durability is a concern, we are the same as the concrete without carbon dioxide, with the added benefit of reducing the concrete carbon footprint by somewhere between 17 to 20 kilograms per cubic meter. My coordinates are here. If you wish to connect by email, by phone, if you wish to discuss what the financial and/or environmental impact of our technology is, I look forward to hearing from you. Thank you so much.
Pak Hari, masih di mute, Pak.
Ya.
Terima kasih.
Thank you, Mr. Kaya. It's nice to hear about the technology, and your market is already US, yeah, all of US. I see. That's good, and Australia also, yeah. So yeah, let's think about our opportunity, yeah, if we apply to Indonesia. Okay. Next Q&A is after all the presentation, the papers, yeah. So the second presenters is Mr. Matthew Denton from Jayatech Scientific Incorporation. He's international channel manager of Jayatech Scientific, with supporting Europe, Middle East, Africa, and Asia region. Based in Cape Town, South Africa. Matthew has been active in the industry, supporting partners with his 18 years experience in supplying the construction industry with the latest in concrete testing technology. With Jayatech, Matthew is now addressing the current challenge in concrete testing, analysis, design, and production by implementing smart technology that monitor concrete properties and analyze data during design, production, delivery, placement, and service. Okay, time is yours, Mr. Denton.
Thank you very much, sir. Thank you very much. A pleasure to be here, and always an honor to be a part of such a great direction, you know, as a unified group of people in the industry, and really to have this sort of positive impact. I think, you know, we have to be thinking about the future. We have to be thinking about what is next. And I think this is certainly one of the most effective ways to be doing that. This morning, it is a pleasure. I'm going to be presenting a short presentation. We have a lot to say, and I'm going to push through some content, but of course this presentation would be available, and I know we've discussed distributing that, so I look forward to putting that through to you. I'm going to just share my screen now, and hopefully if there's any questions or Q&A, just pop them in the question blocks there, and I'll be happy to answer as much as we can at the right time. All right. Okay, so let's start with that. I just want to make sure that everyone can see the correct screen. I'm going to ask my panelists, they're the only ones I can see. If I get a nod from someone that can see the correct screen, excellent, great. Okay, so we are Geotech, going green with Geotech. As Mr. Harry said, my name is Matthew Dent. I'm the channel manager for Asia EMEA, and I do operate out of Cape Town. So I'm coming to you from a sunny Cape Town. The sun has just risen here in South Africa, in Cape Town. And it's absolutely a pleasure to be here this morning. So if we talk about Geotech quickly, just to start off, as Mr. Harry mentioned, our vision really is about revolutionizing the concrete industry. One of the things that we see is critical and essential to this is, of course, the collection and the information around concrete. So, our vision here is really to give everyone in the industry a clear picture of the full life cycle of concrete. So from the batching to the pouring to the curing on site, and of course then the longer term monitoring of concrete as we move forward in the industry. Today's agenda is a couple of points that I'd like to, and I know this seems like a lot and many points to go through in a short amount of time, but I will try and keep to the track. But we're going to be talking about maturity very quickly and very briefly. This is a concept that is familiar to some, not so familiar to others, and this is certainly quintessential to the conversation that we're going to have today. We'll talk about that. We'll talk about how we can save time using this method. But more importantly, today is really about how we can make a change in the environment. If we're working a little bit smarter, there's certainly a lot of things that we can do to improve our carbon footprint as a construction industry in the world today. Concrete maturity, we're going to talk about the cold weather energy savings, a little bit about Geotech behind the green logo. And then, of course, I think one of the things that really is a hot topic nowadays is artificial intelligence, and of course, how we can apply that to concrete. If we have time as well, I'll present a little bit of a demo on some of our software. But if we don't get to that, that's okay. I'm always available and to set up a presentation to those who wish to have some. So if we jump into the first topic quickly, what is concrete maturity? Concrete maturity is a method of us, another method that we can use to measure concrete strength. So at the moment, there are three main methods that are out there in the market for us to monitor concrete strength. So either we can do field cured samples or specimens, whether it's a cylinder or whether it's a cube in your market. That can obviously change from market to market. That is when we take that sample, we keep that on site to try and replicate site conditions for that element. And we would then cure that in similar conditions to what is happening on site. The second one is, of course, lab cured samples. And this is something that we're very familiar with. This is pretty much the standard practice around the world in every market that we talk to, in every industry around the world, is to take a sample of the concrete that we are pouring on site, put that into a controlled environment, a curing bath, water bath, whatever it may be, and maintain that at standard temperature. And then from that, we can compress that sample and we can determine the MPa of the concrete. And then the third method that is becoming more and more growing trend is maturity method. And that's when we measure the real-time temperature on a continuous basis to determine the strength. So let's just have a look at where this comes from and the method comes from very briefly. And that is that when we look at this graph here, you'll see that there's a big difference between the temperature of the concrete placed on site versus your lab cured sample versus your field cured sample. And so here you can see our green line is that sort of spike if we're monitoring the concrete temperature of our poured concrete. So whether this is a slab or whether this is a column, this could be a 100 millimeter slab or a 200, 300 millimeter slab, we're certainly going to see a difference between the temperature on our poured concrete, on our on-site concrete versus the temperature of our concrete in the sample. So in the smaller element, in the smaller sample, there's a big difference there. Many of the limitations around this, and again, I'm not going to spend too much time on this, is where the focus is today, of concrete cylinders or concrete cubes in your particular industry, is that we don't really have an accurate representation of the concrete conditions. There's sometimes delay in results. There's also limited information. When we're just taking this one sample, it's only giving us a snapshot of what's happening in that concrete. And of course, there's local variations. One of the challenges we see around the world as well is the challenge behind the quality control of these samples. They're so significant, yet minor differences can have such a huge impact on the results that you get from those samples when you send them to the lab and for them to be crushed for results. And of course, this gives us a very low visibility of what's really happening on site. So when we talk about maturity, maturity is the relationship between that change in temperature over time to the strength. So you'll see there's a value here that is perhaps a bit unfamiliar to many of us, and that is the maturity value, and that is the degrees Celsius over hours in relationship to what our strength is doing. So our MPa here, as we can see on the MPa line, that relationship is consistent for a particular concrete mix. And this is the standard. It's an ASTM standard, it's an EN standard, it's a standard adopted in many countries around the world, where they're using this as an accurate indication to what the concrete strength is on our construction sites. Just to sort of briefly mention this as well, is a number of applications for maturity really are pretty much, and I'll summarize this whole list, is wherever the concrete strength is critical, the information of the concrete strength is critical, this is where concrete maturity is applicable. So 9 times out of 10, whenever we're worried about the concrete strength on a construction site, and that is the critical path for that program or that project, concrete maturity will play a significant role in that. If we talk about the time savings regarding this, and we're talking about the bigger picture of saving time on a program, saving time on a schedule, let's have a look at a quick comparison between when we're using the maturity method versus when we're using our standard sample collection and compression data. So here's 2 graphs for us to quickly have a look at. And again, I'll show you the difference here. We have on the left-hand side, we have a graph showing the in-place concrete strength versus your lab cured sample. So what's happened here is they've taken a lab cured, they've taken a sample on site, they've put that into a cube, they've sent that to the lab after 24 hours, and that's cured at a constant temperature of around about 20-25 degrees here, which is fairly standard practice. Whereas on site, this was a particularly warm climate that this sample was taken. You can see that the spike in temperature in the first 12 hours was much greater on our element on site. In this particular scenario, it was a slab that was poured. So what does this result in? This results in a very different temperature and strength gain in our in-place concrete. Here in the black line, we can see on this graph on the right that our early age strength spikes a lot quicker. It does plateau out towards the end again than our strength that we gained from the cube sample. So if we have to look at that in the scenario where we're worried about 31 MPa, we're trying to reach a target strength, as you can see here on 24 hours, we're reaching a 31 MPa on our in-place concrete. So that's the in-situ concrete. So that's the concrete on site versus where we're taking a sample from the concrete and crushing that in the lab. We see that on the same timeline, on 24 hours, we're only reaching a 25 MPa strength. So you can see that there's almost half a day difference between the same strength results from the same concrete. And of course, the key here is that it's that spike in temperature that we see as a big difference. All right, so again, field cured versus in-place strength. I don't want to spend too much time on this slide, but it's essentially what we're saying is that because of the field cured samples that we're taking, they're much smaller, they retain much less heat, and therefore the difference between the field cured and the in-place is that massive spike in the temperature that we often see in the first 12 to 24 to even 48 hours in many cases. All right, I'm going to jump forward a little bit here. I don't want to spend too much time here. So again, if we do a quick comparison here, we look at this scenario here, where we have this sort of spike in the early temperature gain on the in-place concrete in our green line. Our blue and our red line are samples that are taken. The red line is the sample of the cubes kept on site. So we can see quite a difference in the maturity line. And I think one graph that we're all familiar with here that we talk about today, if we look at the strength graph, you can see that that earlier age strength graph is a much quicker gain, and then it sort of plateaus out, whereas we're actually getting very different strength curve from the sample that's taken on site versus the sample that's on the field. So just to quickly show here, if we have a look at this graph, we see there's an in-place concrete, we see lab cured, and we see field cured. And you can see in that early age strength, in the 24 hours, we're almost a 17 MPa difference on the first day versus 72 hours. We see that the difference sort of changes. It's not as drastic, but we see still that there's a greater strength in the concrete on site versus your lab cured sample. So the question we have to ask here is that if that is telling us a different story to what our samples are telling us, where can the cement savings come in? What can we do to reduce our CO2 if this is the case? Oftentimes, we're over-designing our mixes to be safe. We're over-designing our strength on our concrete mixes to make sure that we cover ourselves because we're using a method like crushing samples, like crushing cubes, as an indicative sample of what should be happening on site. And we know the liability, the issues around that are always a big factor. And therefore, we always adding that extra safety factor. We're always over-designing our mixes just to be 110% sure that we're hitting our strength. But with the right data, with the right information, with real-time data, we are able to make a difference, have an impact on the amount of cement that we need for our standard concrete mixes. Now, I'm going to say my colleagues from Canada in Carbon Cure, they're doing some amazing work with putting that CO2 back into the concrete, and it's incredible. And I'm very excited to see them growing so rapidly around the world, because really those are the companies that are going to make a big impact in the long run here. And from our side, the information is what we believe and where we come from. And we've spoken about IoT and information and collecting of real-time data. This is where we see that we can have an impact here. With the right information at our fingertips, we can make smarter decisions about the concrete that we're using on site. You've heard all the facts, you've heard all the information about how cement has such a major impact on our CO2, that is such a major contributor into the market in Indonesia. And let's have a look at a particular example. I'd like to jump straight into this. And this is a post-tension deck for a project that we were involved with. We had a look at the scenario and we said, okay, let's take the project. Let's see what we could really do here. And this is now becoming a very common trend for us. We see this again and again in our customers. So there was a design strength of 40 MPa. However, the target strength for the post-tensioning was 20 MPa. So if we break down this, we look at mix one, we look at the mix proportions that we had, the kilograms per cubic meter of cement, the kilograms per cubic meter of water, and what that water cement ratio. Fairly standard mix, not too complicated here. And when we look at the 3 days target strength that we had was 20 MPa. And when we actually started reading the information from the concrete sensors, so our smart rock sensors that were placed in the concrete, we realized that there was actually a 4 MPa difference between the target strength that they were aiming for versus the actual strength they were achieving on site. What did this allow us to do? This allowed us to use and put this information into our system, into our AI, into our dashboard, our 360 dashboard, which in turn allowed us to, our AI was able to spit out the information that we could actually reduce the cement by 4% and keep the water cement ratio. So we kept that workability. We didn't want to affect that, but we wanted to see how could we reduce the cement that was actually put in here. This allowed us to actually come out with a different cement value of 340 kilograms per cubic meter. Our water stayed the same. So our water cement ratio changes just a little bit there. However, now our target strength, or at least the strength we were actually reaching on day 3, was 22 MPa. So we're about 10% above the target strength, which gives us a good performance versus that overperformance that we were expecting. What did this result in? In the end of the day, what we had is we could reduce the actual cement required per cubic meter. So it's a very basic equation. We could say, okay, so from 355 to 340, we reduced 15 kilograms in 500 cubic meters of concrete. That worked out to be 7.5 tons. And of course, in that scenario, we're talking about a 6.75 ton CO2 savings. When we go to the entire project, this particular project where we did this scenario, we had 15 floors or 15 stories in this particular project that we looked at. We had 2 pours per story. The pour volume was 500 cubic meters. The total volume was 15,000. This resulted in a savings of 225 tons of CO2. Of course, this is a fairly theoretical calculation, and of course, there's many other factors that have an impact here. But when we talk about the straightforward savings that we could bring to the party just from being more efficient, economical in our cement usage. When we take this a little bit further, and I want to show a couple of slides here very quickly, when we start thinking a little bit bigger, again, this is a very rudimentary, possibly, way of thinking, but I'd like to just point this out, and I think that, again, my colleagues here who are going to talk about carbon upcycling, recycling, and carbon cure, what they're actually taking the CO2, putting that back into concrete, it's incredible. But when we look at our whole life cycle of the concrete, one of the things that we see as a huge factor that plays a role here is this aspect here of actually collecting these samples, transportation to lab, breaking these samples. And again, here we're talking about cylinders, but of course, in the Indonesian market, we know that common practice there is for cubes. And this here we see, I've just had a conversation with one of our bigger projects in Europe, and they've done a calculation on the amount of cubes and samples that they have to take for the project. And we're talking about hundreds of thousands of tons of concrete here that are going to be spent on just samples and taking samples. And so our vision here really is to be able to just have small changes here and there where we can reduce these unnecessary requirements that we have on site when it comes to concrete testing. We're looking, and this is the bigger picture here, is that we can replace that whole scenario and that whole sample of having to take all those samples, taking them to a lab, crushing them at a lab, with using smart technology like our smart rock, for example. So on the bigger picture, on the bigger scale here, as rudimentary as it may be, we can reduce the number of samples that need to be taken. We reduce the number of trucks and transport that needs to take to get that sample to site, and of course the cement as well. I'd like to give another example here, and this is probably very in line with it's part of the same project that we looked at. And there's a lot of information on these slides. This presentation will be available, and I'm happy to share this as well. But if we just look at the samples, just from saving the number of samples that are required currently on site, and oftentimes we're taking that early age strength samples that we know if we can either tension the deck or we can strip out our formwork. These are all factors that play a big role here. Whereas at the end of the day, if we can reduce the number of samples taken, we can have a look at how many cubes we could save. In this particular scenario, is slightly different. We had a look at the number of cubic meters of concrete, the standard requirement for how many cube samples are required for the particular project, and how many cylinders or cubes were taken per floor. So on your standard testing scenario, you're talking about 21 to 35 per floor. Whereas as soon as we start utilizing maturity sensors and that smart sort of technology idea, we are able to reduce that. And just on this one project, of a small 15 floor project, we're talking about 210 cubes that are saved. Not cubes of concrete, but actual samples and cubes. And you can imagine, if you're working on site, if you're an engineer, if you're a contract manager, just the logistical hassle and nightmare of having to deal with those 210 cubes is a big problem. And of course, that's something we're very proud to be able to reduce. All right. Another aspect of this, and I won't spend too much time here, is cold weather, perhaps not such a common scenario in Asia, but certainly a slide, and I think the inverse is possibly true as well. But certainly on our colder weather climates where we do have that low temperature, where that has a big impact on the performance of the concrete, a lot of effort and energy is spent on controlling the temperature of the concrete based on the ambient temperature. And again, this is where our sensors, we're monitoring that temperature in real time. This allows those on site to make more efficient decisions about how to control the temperature on site, what external impacts need to be applied there. Again, I mentioned this very briefly, but if we talk about cold weather, our smart rock is accurately monitoring the temperature, allowing us to really be able to effectively monitor that concrete so that we can make the right decisions on site for our concrete. Again, I'll share this as well, you know, in cold weather, especially when we talk about post-tension, you know, stressing cables is a very sensitive operation. We need to rely on accurate data, accurate information to be making the right choices there. And then the last topic that I want to touch on, and I'm going to be running out of time before the moderator kicks me off here, is if we talk about broadening our mindset a little bit beyond maturity.
You have
Yes.
1 minute.
Thank you. That's perfect. That's all I need. I'll be here very quick. Is that when we talk about this, what we need to do is we do need to think about, you know, our durability of the concrete. You know, what is the impact of those high temperatures that we're gaining on our concrete sites, and how does that have an impact? For geotech, the big thing here that we'd like to, and so I'm going to jump through to this last slide here, and this slide here is artificial intelligence in concrete. The big key that we see and the big advantage here is that if we're able to collect accurate data from site, we're able to make accurate decisions on site. And by using things like artificial intelligence, we would be able to effectively reduce our cement on all of our projects worldwide. And let me stop there before we run out of time.
Thank you, Mr. Matthew Denton. It's very interesting about the testing that will give us the effectiveness of method. Yeah, it's we will hope that the method can precisely detect the reduce carbon in our concretes. Okay, yeah, we will save our question for until the third presenter. So the third presenter is Mr. Ryan Ward from Carbon Upcycling Technology. Mr. Ryan is currently the Business Strategy and Development leads for Carbon Upcycling Technology. He has been with Carbon Upcycling Technology for 2.5 years and come to the company following the completion of his Sustainable Energy Development Master's degree. Ryan focused on the commercialization strategy for carbon upcycling technology, core technology and products, while also exploring new regulatory opportunities and initiatives. So the time is yours, Mr. Burns.
Great. Thank you so much for the introduction, and it's great hearing about the work that CarbonCure and Geotech are doing. I think what's very interesting about the different technologies we're providing here is that they all work towards the same goal. It's why we're all here on this conversation. But they're not mutually exclusive. These are things that can work together to create that most optimal mix design and really get to that shared goal that we all have. So thank you very much for the opportunity to speak here. I'm just gonna share my slide with everyone. All right, so as was mentioned, my name is Ryan Borns. I'm with Carbon Upcycling Technologies. We were founded with the vision of using the waste of today to build tomorrow. And I'm calling in from not so sunny and not so warm Calgary, Canada right now. So in terms of the problem that we're looking to address, this will not come as a surprise to anyone. We're looking at global CO2 emissions. And I mean that in two respects. So firstly, there's point source emissions, something that would come off a smokestack that we all see. But then there's kind of that indirect emission source associated with the buildings industry. So the buildings industry is responsible for about 40% of global emissions. And about a third of that comes from the materials and processes, or the embodied carbon of the buildings. And over the next 40 years, we're going to be doubling the square footage of the built environment. So if this is an issue today, it's going to be an even bigger issue in the future. So we wanted to develop a technology that could utilize the point source emissions to improve the materials that are, and hopefully reduce the impact of those materials that go into the buildings industry. And so we've done this with a patented carbon utilization process where we take gaseous CO2 emissions and chemically absorb that CO2 into inorganic raw feedstocks. So these could be materials like I've described here, either fly ash or talc, or other industrial waste like steel slag or crushed glass. So we use that material, like that fly ash, to act like a sponge where it's soaking up CO2. But at the same time, we are exfoliating the surface of it, which starts to resemble something like that sponge there, where there's more surface area and more pores within the fly ash. And the main outcome from that, and the most important thing for our work, is the fact that this creates basically a supercharged, more active surface area for when that material is used in a concrete mix. So this process that we have actually lends itself to a few different industries where we can create advanced materials to be used as industrial additives in the coatings industry, in the polymers industry, with nylons. But of course, I'm gonna speak mostly to our work in concrete today. So this is something that we've been working on for probably the last 3.5 years, and specifically in the concrete industry. And we've been able to demonstrate that with our process, our enhanced fly ash, as we call it, can increase the compressive strength of concrete by up to 40%. And of course, this means you can further reduce cement and reduce the embodied CO2 associated with, or embodied carbon associated with that material. And this is something that's been validated with partners around the world, like Lafarge Holcim, and more locally to us, a local company called Burnco. You'll see them in a picture later on, probably. And so just to give a bit more clarity to our process and what it can actually do, it's a very low energy carbon utilization process. We're using the full CO2 molecule, so we're not breaking the carbon and oxygen bonds when utilizing CO2. We're just putting it into a pressurized, actually the vessel is right there, a pressurized vessel that creates both that agitation and necessary environment to facilitate that carbon absorption by that fly ash. This has allowed us to show that we can reduce cement by up to 20% in a standard mix. And in terms of how much CO2 we're actually getting into that fly ash, it's between 5 to 15% by weight of that end product. So for every ton of fly ash that we have, there's between 50 to 150 kilograms of CO2 stored permanently in that fly ash. This is something that we've scaled up again over the last few years to the point where we went from something the size of a cookie jar to our most recent reactor, which produces about 8 tons per day. And here's, I guess, a couple more pictures to describe this. And this is something that we have at our demonstration facility in Calgary. And as I mentioned, we're producing about 8 tons of product per day at this point. Now, as everyone's probably quite aware, there's a few regulatory hurdles to get into the concrete industry. And this year we, after getting our vessels scaled up, getting our production capacity scaled up, we also went through the necessary regulatory testing that showed that our material is suitable for concrete applications because it resembles fly ash in every sense of the word, except for the fact that it improves performance, both from a compressive strength perspective and from a durability perspective. So because of this approval, we're now just getting into commercial projects at this time. And as I mentioned before, because of the enormous increases in strength that we're showing, we don't need projects to be 40% stronger than they're specified for. As Matthew mentioned, there's a very thin margin that you can work within, and 40% is way above that. So what we really want to show is that because of that strength improvement, we can really reduce that cement that would be associated with it. And this is something that we're still working and optimizing with our concrete partners on. But really what we've shown here is that we can keep all of your, the necessary considerations for concrete the same, whether it's air entrainment or workability, but with improved strength and reduced cement. And this is something we've shown in these commercial trials. Just to give a bit of, I guess, a visual representation of where we are with our facility. We're basically in the backyard of a natural gas power plant. So we take the waste CO2 emissions from that power plant and basically bring that into that large vessel that I had shown you a couple slides ago. And so we're doing this all on site and then sending that, the product that we create, our enhanced fly ash, we're sending that to our partners, our local ready mix partners, for them to do their commercial projects. But again, this is something that we can do either on site with waste CO2 emissions, or in I guess, a less centralized opportunity with delivered CO2 as an option as well. And I'm just going to end off my presentation here, showing a little bit of our international traction. And now, I know we have a handful of commercial projects that we've been involved in, but because of just the ubiquitous nature of this material and the impact that it has around the world, we've seen a lot of attention in the last little while for our technology to deploy it into different strategic locations. So a few partners that I would like to give mention to here. So we recently announced a partnership with CMX Ventures, their group in Europe. And what they're looking for is for our technology to improve and perhaps bring new supplementary cementitious materials into the market. And this is something that we've shown with other industrial waste products, where we can actually make them a suitable material for implementation into concrete. So again, we're reducing cement because of this, but we're also using more waste. We're creating that circular implementation to go. So we're excited to get those projects underway with all of their different SCMs that we're looking at. We've also will be taking part in a European funded project, again looking at CCU, or carbon capture and utilization, for a cement company. And recently we have been working with IHI, the large Japanese consortium, and we're co-evaluating some opportunities for our technology to work with their different business units. And of course, IHI has an enormous presence across many countries in the Asia Pacific region. And so our technology has relevancy to a lot of their different markets and industries. And I'll wrap things up there. Again, very excited to talk in further about our technology here in terms of how we can help reduce the carbon footprint associated with concrete. Thank you.
Thank you, Mr. Ryan. Yeah, interesting, yeah. Upcycling, yeah, not recycling, yeah. Upcycling. So you improve cycling concrete, yeah? Is correct?
That's correct. Yeah. Yeah. Take it one step further than recycling. Improve its existing state.
Okay. Nice presentation, and we almost always happy, yeah, to hear new technology. So yeah, we will now in the Q&A answers. There's so many questions from the audience. I will choose for one of you. For Mr. Kaya from Arifatunisa. Mr. Kaya Salowski, how to know the CO2 have enough in concrete, and how to know all of CO2 to be connected to make CO2?
So it's a good question. The dosage of carbon has been developed through many years of research and over 4 years of commercial activity. So during commissioning, when we start with a concrete producer, we evaluate the cement blend that they're using, and we dose somewhere between 0.2 and 0.35% by weight of cement. So if we think of a cubic meter of concrete, we're able to sequester somewhere between 700 grams and 1 kilogram per cubic meter. When we've tested our technology in a vacuum, we have found it to be approximately 92% efficient, meaning that approximately 8% of the carbon is lost to the atmosphere, but 92% of it is mineralized permanently in the matrix of concrete.
Okay, I hope your answer satisfies the Mr. Fina. Eh? Okay. The second question for Mr. Matthew Denton from Mr. Zulfitrian Saputra. Oh, this is Indonesian. I translate, yeah. If application based on this cellular need update and calibration regularly before it use. Okay. And the second is how much coefficient tolerance of the result of the forensic structure measurement?
Sorry, could I just ask that question again? So it sounds like there's two parts to that question. I just want to clarify.
Yeah, there's two questions. Yeah. Okay, I repeat. Okay. The first one, if the application of a cellular base is need update and calibration before it use. That's the first question.
So
update and calibration, yeah. And okay, the second, what's the tolerance coefficient? Oh, the first question. Okay.
Yeah, maybe just before so otherwise I forget. You know, in my old age, I forget these questions, so I have to answer one at a time. So for the maturity method, there's always a calibration required up front. You just need to do that calibration once per concrete mix design. So if you're using the same concrete mix design on your project, you're going to only need to do one calibration. If you're extending that usage of that mix over a longer period of time, then a good practice would be to validate that calibration every so often on a regular basis. So there is that. So you have a calibration in the beginning, which is very much like a standard strength test, and then a validation, which is really just adding another sensor to your existing strength tests. I hope that answers the question. And then the second question. Sorry, I'm sorry. I think you're muted.
How big, how much a tolerance coefficient from the structural measurement? Tolerance.
So if I understand the question correctly, you know, the difference between the maturity method strength results versus our standard testing strength results?
I think it's the tolerance of the measurement of your device. Yeah.
All right, excellent. Okay, so with regards to the maturity method, and I think this is important for me to say as well, is, you know, the maturity method is a very standard practice that's been adopted around the world. We're not inventing a new method to testing concrete. So our device, you know, there's no secret sauce here. It is really just a temperature device. And then the calculation of strength from the temperature based on maturity is accurate to within 1 or 2 MPa. So, you know, it is all about the accuracy of the calibration, but within a few MPa, you are accurate to that strength.
1 or 2 MPa, yeah? Okay. I think it's accurate enough, yeah? Okay. Let me select for the Mr. Ryan. Yeah? It's ready from Mr. Ryan. Okay, this for Mr. Ryan from Harley Muhammad Hafil. Very interesting that carbon technology can increase the concrete strength and reduce cement. But one of our consideration is cost. Can you explain in one example that compare cost estimate carbon tech concrete versus basic concrete? Is it clear, Mr. Ryan?
Yeah,
I think comparison
so.
Cost. Yeah.
Yep. No, that's perfect. And that is a great question. With any new technology, that's got to be your first question. So I appreciate that. And I think the most important thing that we, I guess I have to put a few caveats around this answer. Depending on where in the world we're looking at this opportunity and the cost compared to cement and fly ash, for example, that I guess there's more favorable opportunities for us. But locally for us, there's a relatively high cost of cement and a less expensive cost of fly ash. And we're seeing that we're essentially cost neutral for our concrete partners. And this has to do, obviously there is a cost premium on the fly ash that we produce compared to just standard market fly ash. But the fact that we're able to reduce the cement by an additional 10% or more, that's where the cost savings really play in for the concrete partner. So it's an intentionally vague answer that I'm giving here, but I think it's the most important thing that I would like to emphasize, the fact that they're depending on the difference between cement and other materials. That's an important consideration for our cost.
Okay. Are you sure can we apply it in Indonesia also? Mr. Ryan? Hello? Mr. Ryan?
Oh, yep.
Can you sure that can be applied also in Indonesia?
Can this be applied in Indonesia or the cost comparison?
The cost.
Yeah, that's actually a perfect question. We're evaluating that opportunity right now. And what we're seeing is that it would be one of the most favorable regions for us to deploy our technology. So it should be a cost neutral opportunity for us, just because the local cost of fly ash is quite low across Indonesia. So it's a great opportunity for us from what we've seen.
Okay, let's see if our audience in Indonesia will follow up, yeah, the informations. Okay, thank you, Mr. Ryan. So I'm back to first presenters. I will choose the question. Okay, from Mr. Alda Rafadana. For Mr. Kaya Salowski. Questions. Thanks for the opportunity. My question is, with same concrete job mix formula, how much percentage of increase of the concrete strength with additional of CO2 mixtures?
Yeah, so it's an excellent question. Our value proposition is tied to the reduction of cement, because through the reduction of cement, we can reduce the embodied carbon of concrete. So the gentleman, I believe, was asking if we did not reduce cement, what would be the impact on the concrete? So adding this very small amount of nano calcium carbonate will, in general, increase the compressive strength profile by 10 to 15%. And that's where most concrete producers take advantage of that strength gain to reduce the binder content. So they reduce the cement and the cementitious, and thereby reduce the carbon footprint and maintain the required strength.
Okay, thank you. I think it's
good question.
Yeah, and good opportunity also, yeah, that we can achieve something like that. Okay, I move again to the second presenters, Mr. Matthew. This is from Toba Oha. How long is the lifetime for the strength of 40 MPa from the cement saving production of PT deck example can survive, and how to manage waste from unused cement savings? Is it clear, Mr. Matthew? I repeat, yeah. How long is the lifetime for the strength of 40 MPa from the cement saving production in PT, yeah? Oh, post tension, yeah? PT, yeah? Deck example can survive, and how to manage waste from unused cement savings? Is it clear question? Please unmute the mic, Mr.
Sorry, I'm muted. Sorry about that. So just to clarify, so they're asking about in the 40 MPa sample with the post tension sample, what to do with the additional material that we're saving.
Yeah. How to manage the waste from unused concrete, unused cement saving? How to manage waste from unused cement saving?
So I think, remember so if I understand correctly, the question here is, the idea from our side is to manage that beforehand. So when we're doing that design mix, correct, before. So the idea here is that we're able to take a mixed design, put those mixed proportions into our AI, and that would actually spit out that cement reduction beforehand. So it would actually provide you those results and that information up front, so that you'd be able to actually reduce that cement input from the start of the project, and therefore be able to reduce your CO2 in the long term. And if just in case, if the question is referring to the additional samples that should be taken, the conversation there again is about having that concept of, if we're using the maturity method, and I saw one of the other questions, and maybe I'll just say this quickly as well, is that when the code requires certain sets to be taken, that certainly is adhered, but sometimes it takes a moment to look a bit closer at the code, because the code often talks about when no other information is available. So when we bring in the maturity method, we can just reduce the number of samples required to be taken. So you only need that 28-day sample to be taken, but for the early age, 7, 14, possibly 3 days on post-tension, you're actually able to reduce that and take those away and replace them with the maturity, even based on a code that you might have that specifies that.
Okay, thank you. Mr. Matthew. So I choose for the circuit answer. Yes. Okay. This is for Mr. Ryan Burns from Miss Happy Nuritasari. When the carbon-induced concrete arrive on site, if the concrete start to harden or the slump doesn't fulfill the requirements, is there any treatment additive made specially for carbon-induced concrete, or can we edit common treatment additive?
Sure. So just to make sure I have the question right. So I guess firstly asking if there's any workability issues prior to getting on site, and then are there any special additives required if that's the case?
Yes. Yes.
Perfect. So yeah, we see a very minimal change in terms of the slump or the workability in the concrete, and if ever I guess the project itself requires a bit of a change in that slump or workability, just the same standard additives can be implemented into that project. So the same plasticizers for air entrainment, same air entrainment agents, everything like that can remain just the same as any ready mix partner would do with their standard mixes. But there haven't been any concerns with the I guess the product getting to site or in between the plant and getting to site in terms of how that the workability changes within the truck itself. So we haven't seen that as a concern or consideration, but if there were, the standard concrete additives could certainly be implemented.
Okay. I think it's very clear. Yeah, we have still time, yeah, Miss Farah. Okay.
We still have 10 minutes. Pak, silakan.
Ya, berapa menit lagi?
Kita masih bisa 10 menit lagi, masih oke, Pak.
Okay. Let's move to the first presenter, yeah, for Mr. Kaya. This is the question from Yudi Tanuwijaya. What is different carbon cure technology compare if we add CaCO3 direct? Or in the world, we can use CaCO3 to reduce cement and fly ash.
Another educated and excellent question. What we are creating in the mixer, whether it's in the back of the truck or in the central mixer, is a nano calcium carbonate, so nano CaCO3. And the question compared the natural limestone that can be added into a cement blend or into the concrete as a supplementary cementitious, right? Similar to your fly ash and your slag. So the size of the grain of cement that you're adding is still visible to the naked eye. The size of the particles that we're creating in the mixer are roughly 400 nanometers in size. So they are invisible to the naked eye. You can only see them with a scanning electron microscope. So if you think of it this way, the science around seeding concrete with small particles to deliver improved strength is well understood, right? That's one of the basis of the use of products, waste products like silica fume, for example, as a densifier or as a strength improver. So what we have proven, and we have many white papers and studies to show this chemistry occurring, is this fine precipitated calcium carbonate, those 400 nanometer sized particles, are the ones that are causing that seeding effect. The early sites of hydration are directly linked to those particles. And when you take early strength testing, whether it's at day 3 or day 7, we're seeing somewhere between 10 to 15% improvement in compressive strength. So back to the question, the type of calcium carbonate that you're adding in your cement blend is a much, much larger particle than the one that we're making in the mixer.
Okay. Thank you, Mr. Kaya.
You're most welcome.
Okay, back to the Mr. Matthew. This is from Alvina Arifatunisa. What the maturity sensor is tepat is the what the maturity sensor is precisely measure, although the heaters is not enough yet.
So I'm gonna take some liberties here to try and understand the question clearly. So the maturity sensor, tepat is, so the translation of that word is right?
Right, yeah. Precise measurement. Precise measure.
Accurate.
Accurate,
Okay.
yeah. Accurate.
Okay. So the maturity sensor is accurate, although the heaters is not enough. So I'm going to elaborate a little bit on which is fairly a common question here with regards to curing or managing the concrete temperature. In often cases where we've got mass concrete or bigger elements, or perhaps in a precast, I saw one of the questions that came up about steam curing. And the reality is that with the maturity method, what you are doing is you are monitoring the concrete temperature in real time. The information comes directly to your smartphone. It's immediate. You get it in real time. And so therefore, you're able to know exactly what your concrete temperature is doing on site, and you will be able to make decisions around the curing of that concrete. So whether you need to put heaters on the outside, or whether you need to cool it on the outside, these are all different decisions that need to be made based on what is happening with your temperature inside your concrete. And that's one of the things that comes with maturity, or using a maturity method, is that real-time temperature monitoring. And irrespective of whether your concrete temperature is going to 80 degrees or whether it's going to minus 10 degrees, the maturity method is going to give you an accurate indication of what your concrete is doing. So there's two aspects there. One is that you're able to make accurate decisions on how to maintain the concrete temperature, or positively affect the concrete temperature for whatever the scenario may be. And two, that you're actually knowing what your concrete strength is doing based on the actual on-site information that's provided. I hope that answered the question. Sorry, Mr. Harry, you are on mute again.
Okay, thank you. So next question for Mr. Ryan Burns from Maradel Sijabat. Some cement manufacturers have added fly ash to their product. How do we predict the addition of fly ash to concrete manufacturing?
So I guess in terms of if there's already a blended cement being added, how would that change the amount of fly ash to then go into the mix? To be honest, I don't believe we've actually come across that particular question or that particular mix design at this point. I think in terms of what that blended cement would be, they would have their own percentage associated with that. That could then we could easily then make that calculation for how much additional SCM we'd want to add to the mix. So it is dependent on how much fly ash is blended and what are the performance specifications around that. But in terms of it being compatible with blended cement, it would certainly be just as effective.
Okay. Yeah, for your information, now in Indonesia, the cement manufacturer have produced many blended cements. Yeah. So I don't know if in the Canada is the manufacturer is direct. Usually the use the blended cement in the manufacturers, or just a plain.
Yeah, sorry for cutting you off, but yeah, I see where your question was heading there, and it's not very conventional, I would say. We do have some partners in Canada who are using blended cement, but for the most part, they're using the cement that's provided to the market is a pure blend.
Okay. Gimana, Mbak Farah? Masih ada waktu?
Sudah, saya rasa Pak, mungkin boleh sudah di-recap Pak. Terima kasih.
Okay, thank you. Okay, ladies and gentlemen, we have finished the presentation and so many questions, yeah, so many questions that we are sorry that we cannot ask all of your questions to our distinguished guests, but there's a very interesting discussions, and I think the attendant is most of them is very educated engineers, yeah. So can give a good question, and we have a very good discussion to know the advantage of that technology that the Canadian will introduce to Indonesian. So we hope this is not the last. This is not the last meetings. We hope that it's just the beginning, yeah, to cooperate between Indonesia and Canadian expert and technology or science in the construction concrete industry in order to participate in the climate change plan, yeah, for Indonesia and Canada. Thank you. I will give back to the Ms. Farah. Thank you. Thank you for all presenter from Canada.
Okay, thank you very much, Pak Hari, and thank you very much to all our speakers. It was a pleasure to have you all with us, and we hope everyone is enjoyed this amazing discussion. And before we end the session, we ask for all the panelists to do a virtual photo, which will be taken virtually by organizer. Please make sure your position is in the center of the frame. Okay. Okay, counting down in 3, 2. Sudah? Okay, everyone, can you check your position? Okay, Pak Hari, sudah siap?
Okay.
Okay, in 3, 2, 1. Okay, once more. In 3, 2, 1. Okay, thank you, everyone. And also, I would like to inform for further information about the technologies presented today, please contact the Embassy of Canada. Their email is jkrtatd@international.gc.ca for possible B2B program meetings. And for all participants who wants to get e-certificate and presentation materials, these are the procedures you should do. First, please scan the barcode on your screen, then fill in the form provided with your complete personal data. The names written on the e-certificate will be based on the data you have submitted. E-certificate and the presentation materials will be sent via email no later than 10 working days. An incorrect name and email address is beyond the responsibility of the committee. So please make sure the data you submit is correct. And don't forget to join the digital exhibition conference of Indonesia Innovation Theory, Konstruksi Indonesia and Beton Indonesia 2020. This digital exhibition can be accessed through the Digital Infrastructure Connect platform from 21st October to 3rd December 2020. Register yourself at infrastructureconnect.id to get an access and win an attractive door prize. And for more information, please contact us at connect@tarsus.co.id. Tidak lupa, saya ingatkan, kami juga memiliki sesi siang ini pada pukul 14.00 sampai 16.00 tentang inovasi dan teknologi dalam pembangunan infrastruktur strategis di Indonesia. And that's our webinar event this time. See you again at the next Infrastructure Connect digital series. Once again, thank you for joining us today. Best wishes for us all.